The existence of the exponential function is we are going to discuss in this video. The existence of exponential functions as well as the uniqueness of exponential functions, some properties of exponential functions we are going to discuss here. So with that regard, the first theorem that we are going to discuss is there exists a function e from R to R such that which satisfies the two properties. The first one is the derivative of the function itself for all x belongs to R, and second one, the function is non-zero, in particular e of 0 is 1. So this statement tells you that there is the existence of the function which is non-zero and the derivative is itself. And we will use the tools of uniform conversions to prove this statement. So to prove this one, we are going to define one sequence of polynomials which converge to this e of x. And that sequence I am defining in this manner. To define the sequence en of continuous function as follows. E of 1 of x is 1 plus x, and En of x, or I can say En plus 1 of x is 1 plus integration from 0 to x En of x dx. For every n belongs to n and for every x belongs to R, we will define this sequence of continuous function. It is clear that this E1 is a continuous due to it is a polynomial function, so it is an integrable over any bounded interval. Same way this En, as it is defined using the fundamental theorem of calculus, it is also continuous and also it is integrable. So it is integrable over any bounded interval. So what we can say is this En plus 1 is well defined due to the fundamental theorem of calculus. And also we can say that this En plus 1 is a differentiable at any given point. So let us write what I have told you, that clearly E1 is continuous on R, and hence it is integrable over any bounded interval. If En has been defined and continuous on R, then it is integrable over any bounded interval. So En plus 1 is well defined. by fundamental theorem of calculus, we can say that this En plus 1 is differentiable at any given point. And En plus 1 derivative will be En of x for every n belongs to n. That we can definitely say due to that. Now, if you apply the induction on this En, like E1, we know that it is E1 of x is 1 plus x. As per the definition, E2 of x is 1 plus integration from 0 to x E1 of t dt. So this is 1 plus x square by 2 factorial. We can easily compute by integration. That means E1 is 1 plus t. To integrate 1 plus t, it is t plus t square by 2. Put this limits, you will have this. Then similarly, one can compute what is E3 of x is 1 plus x square by 2 factorial plus x cube by 3 factorial. And in similar manner, by induction, one can prove that En of x will be 1 plus x square by 2 factorial up to x power n upon n factorial for every x belongs to R. Ultimately, what we have to prove, this En will converge to the function which we required uniformly. So actually we are using the Cauchy's criteria to do this. So for any m which is greater than n and all x which are less than or equal to a, where a is any positive number to be given, we'll start with emx minus enx. If I can prove that this will tends to 0, then we are through, because in that case this En is an conversion, and due to the Cauchy's criteria, it is uniformly conversion. So what is this Em minus En? Em is 1 plus x square by 2 factorial up to so on x raised to n upon n factorial plus x raised to n plus 1 upon n plus 1 factorial up to x raised to m upon m factorial, because m is big. So in between there is n is there. Then it is minus 1 plus x square by 2 factorial up to so on x raised to n upon n factorial. Now this quantities will get cancelled out. The left quantity is x power n plus 1 upon n plus 1 factorial, x power n plus 2 upon n plus 2 factorial up to so on x power m upon m factorial. Now you note that this x power, and using the triangle inequality, x power n plus 1 is get common, n plus 1 factorial is left. Inside bracket we got 1 plus mod x upon n plus 2 mod x square upon n plus 2 n plus 3 up to so on mod m minus n minus 1 upon m factorial. Now what we have assumed is mod of x is less than or equal to a. So due to this, we can write this as a upon a raised to n plus 1 upon n plus 1 factorial 1 plus a upon, now here 1 upon n, because n plus 2 is bigger than n, so therefore 1 upon n plus 2 is less than 1 upon n. So this 1 upon n plus 2 I can write it is less than 1 upon n plus a square by 2, a square. Again this 1 upon n plus 2 is less than n, and this again n plus 3 is there. For that also we can write the same quantity which is less than n, 1 by n. Power n plus 1 upon n plus 1 factorial. So finally we'll have 1 plus a upon n plus a upon n whole square up to so on a upon n whole power m minus n minus 1. Now if I consider this m is greater than n, which is greater than a to a, therefore a upon n is less than 1 by 2. Now if I take the limit here, that is this m minus n is tending to infinity, then this I can write down, or I can just add more terms here. So I can write this is less than n plus 1 upon n plus 1 factorial 1 plus 1 by 2 plus 1 by 2 square up to so on 1 by 2 power m minus n minus 1. So what is the condition I have taken? I have taken that m greater than n greater than m to a. So that I can write down for all this value we have here. We can say this. Still this is greater than or equal to a plus n upon n plus 1 factorial. Why it is only finite terms? I can add more terms into that. That is 1 by 2 plus 1 by 2 square up to so on 1 by 2 power m minus n minus 1 plus the next term up to so on. So this is an infinite series, and we know that the infinite series with the geometric progression having the answer is 1 upon 1 minus r if mod r is less than 1. Here r is 1 by 2. So as per that, this is equal to a upon n plus 1 upon n plus 1 factorial into 1 upon 1 minus 1 by r. If you simplify this, this quantity is 2 times a power n plus 1 upon n plus 1 factorial. So finally what we got is m x minus m nx is less than or equal to 2 times a power n plus 1 upon n plus 1 factorial. Now what is this sequence? This will tends to 0 as n tends to infinity. So ultimately what I am saying is, because summation x power n upon n factorial is convergent. Since this is convergent, its nth term tends to 0. So as n tends to infinity, this will goes to 0. And hence what we can say due to this En is uniformly convergent on the interval which is bounded by -a to a. So En is a Cauchy sequence on -a to a. Therefore, En is uniformly convergent using the Cauchy's criteria on -a to a. And since this a is arbitrary, that means this En of x converges to some function on R. I can say this, since a is arbitrary, in particular, this means that En of x converges for each x belongs to R. Then we define E, which is from R to R, as limit of En of x as n tends to infinity will be E of x for every x is in R. So that is the definition of E which we have. And what we need to prove is this E, it should satisfy two conditions: the derivative itself, and at 0 it will give me one answer. So to prove that it is at 0 it is 0, we note that what is E1 of 0? As per the definition of E1, E1 is 1 plus x. So as per this 1 plus x, x is 0. So E1 is 1. And En, if x is 0, then it is also 1 due to this definition of En. So what we can say from this is E1 and En, both of them are 0. E1 is 0, is 1, and En 0 is also 1 for all n belongs to. And if I apply the limit, therefore limit n tends to infinity, En of 0 is also 1. And due to this statement, that is E of x is equal to this limit for any x belongs, in particular it is 0 here. So that means E of 0 is equal to 1. So that completes the first thing. The first property satisfies. What about the second property, that is the derivative of E of x is itself? If I want to take the derivative here of E of x, then I need to take that derivative inside. So I need to interchange the limit and the differentiation function. So to operate or this changing this limit and integration sign, we have learned one result in the uniform convergence, that if each En is belongs to DAB. What is DAB? The set of all differentiable function on AB. The first condition is each En is differentiable. The second situation is En of at x0 is convergent for some x0 in AB. So for some point the function should be convergent. And the third one is En dash is uniformly convergent. Then we have proved that limit and the derivative you can interchange. So this is the things which we have recalled regarding the interchanging the limit and the integration sign. Now here En is a sequence which we already mentioned that it is a differentiable sequence. For En of 0 we can see that it is converged to 1. So the second condition is also satisfying. And also we have proved that En dash of x is En itself, that we have seen that the derivative of En plus 1 is En. And En is already a uniformly convergent sequence. So En dash plus 1 is also a uniformly convergent sequence. So that means this En is satisfying all the conditions of interchanging a limit and the derivative sign. So to applying this statement, it follows that E is differentiable. E is differentiable. Okay, so we can say E dash of x, that means the derivative of E, which is d by dx of a limit of n tends to infinity, En of x. And if you interchange this, limit n tends to infinity d by dx of En of x. So the derivative of En of x will gives you, as we have just now told you, that it is En minus 1x. The limit of En minus 1x is E itself. And this is true for any x which is in the interval minus a to a, and a is arbitrary. So we have established our result. That means there is the existence of the function which is derivative itself, and at the point 0 it will gives you 1. The second one is a corollary which tells you that not only first derivative, if such function exists, then all the derivatives are itself. So the function E has a derivative of every order, and the derivative nth derivative of this E function is itself for all x's in R and for all n in n. A proof can be done using the induction. So I can, for n equal to 1, we already achieved the results here. And if you use the induction, we can able to prove this. So I'm giving you as a homework to do this yourself. The hint is induction. Second corollary of this result is, if x is greater than 0, then 1 plus x is less than E of x. This is very easy to do. Here x is greater than 0, and we have defined a sequence En is 1 plus x square by 2 factorial up to x raised to n upon n factorial. Since your x is greater than 0, this sequence En is an increasing sequence, strictly increasing sequence. Because ultimately what we are doing, we are adding one term. So for example, E1 is 1 plus x, E2 is 1 plus x square by 2, and it goes on. So what is the difference between this and this? We have added this x square by 2, and x is positive. So x cube term, x power 4, all these terms will be positive, and so we are adding into this. So I can say that we note that this sequence En plus 1x is strictly increasing. So therefore I can write down E1 is the smallest term among all the En for all x greater than 0. And if I apply the limit as n tends to infinity, E1 is nothing but the 1 plus x, which is less than a limit of En is E of x that we have achieved. So if x is positive, 1 plus x is less than E power x. That is, we have done. Now the next thing or next results with which we are discussing about the uniqueness of this exponential function. So the function f or e, which satisfies the two property. The first one is e dash of x is itself for every x is in R, and the second step is e of 0 is 1. Is unique. It means if such function is exist, we have already proved the existence of the e. If it is exists, then that function is unique. It has to be unique function. So I am starting with the two different functions, e1 and e2, which satisfy this both the property. So let e1 and e2 be a two functions on R to R that satisfies property 1 and 2. When I say one property and second property, that means this two property. Now let us define the function f from R to R as f of x is equal to e1 of x minus e2 of x. So I am just defining a new function which is the difference of e1 and e2. Ultimately my objective is to show that this f is a zero function. What we need to prove is this f is a zero function. So let us see what is f of 0. So it is e1 0 minus e2 0. But e1 0 is 1 and e2 0 is also 1. So this is a 0. Since e1 is differentiable n times as per the argument which we have given here, that is all n order derivatives exist, due to this corollary, this e1 and e2 both of them are differentiable n times. So f is also differentiable n times. So we can say that we note that f has the derivative of all order, and what will be the nth derivative of f because it is nothing but the nth derivative of E1 and nth derivative of E2, but E1 and E2 satisfies the conditions, and we already discussed that the derivative itself. So hence it is the function f. So the derivative is itself for any n and for any x belongs to R. Now we'll use the Maclaurin series, or I can say Taylor series at 0, to prove this f function is a 0 function. So let x belongs to R be arbitrary point, any point I'm picking up, and Ix be the closed interval with vertex with endpoint 0 and x. That means Ix is the interval of the type 0x. Now this function f is continuous on this Ix, because f is continuous due to this E is continuous and E2 is continuous. E1 is continuous and E2 is. So f is continuous. So I can say that since f is continuous on Ix, and this Ix is a closed and bounded interval. Any function which is continuous on a closed and bounded interval, it has to be a bounded function. So I can say there exists k greater than 0 such that mode of f of x is less than k for all x belongs to Ix. If this notation is not feasible, you can use the t here. So it is f of t for all t is in Ix. Now we are able to apply this Taylor's theorem on this f in the interval Ix. So by Taylor's theorem, we'll say that f of x is equal to f of 0 plus f dash of 0 into x upon 1 factorial plus f double dash of 0 into x square upon 2 factorial up to so on f n minus 1th derivative at 0 upon n minus 1 factorial x power n minus 1, and the next one is a remainder term, which is f of n, means nth derivative of f at the point Cn upon n factorial x power n, where Cn is a sum point in Ix. Now what we have observed that f is 0, f of 0 is 0, and due to this f n at 0 is also 0, because this nth derivative of f is itself. So all the derivative at the 0 point, it gives me 0 value due to f of 0 is 0. So ultimately what we got from this is f of x is equal to f of 0 is 0, f dash of 0 is 0, f triple dash. So all these terms will tends to 0. Only the last term is that. So that is equal to fn Cn upon n factorial as x power n, due to that f n at x is equal to f itself and f of 0 is 1. Now I will use the boundedness of this f over the interval x, Ix. So mode of f of x is less than or equal to mode of k into mode x power n upon n factorial for all n belongs to n. We can have this. because we have assumed that this mode of f is less than k, and mode of f is exactly the nth derivative of f, so that's less than k, and this will tends to 0 as n tends to infinity due to the same argument which we have given you, x power n upon n factorial is convergent. This will raise to 0. So that means mode of f is equal to 0 for all x belongs to R. Since x is arbitrary, we have this. So therefore f is 0 for all x belongs to R, and since f is 0, E1 equal to E2. So it proves that there exists some function which is having the derivative in itself, and at the point 0 it gives you answer 1, and this function is a unique function. So now we are able to define what does it mean, or what is the definition of exponential function. So our objective is to define now exponential function. The unique function E, which is from R to R, such that E dash of x is equal to E of x for all x belongs to R, and E of 0 is 1. It's called the exponential function. And the number E, that is E of 1, is known as Euler's number. And then the notation that we are using for the exponential function is exp of x or e power x. These are the notations we are using for exponential function. Now there are certain properties of exponential functions that we need to discuss here. So I'm going to discuss that property here. That is the first theorem. The exponential function. So whenever I say the exponential function, that means it should satisfy the two conditions: the derivative itself, and at the point 0 it has the value 1. Following conditions. The first one is E of x is non-zero. That means exponential function is non-zero function for all x belongs to R. The second one is E of x plus y is E of x into E of y for every xy belongs to R. The third property is E power R, that is E of R is E power R for all R belongs to Q. So for all rational numbers we can write down in this manner. The next property, that is E, is a strictly increasing on R, and a range is equal to all y belongs to R such that y is greater than 0. And the fifth one is limit of E of x is 0 as x tends to minus infinity, and limit of E of x is infinitive as x tends to infinity. So these 5 properties, let us try to prove one by one. So when I can say it is an exponential function, it should satisfy only two conditions. Using that, you have to prove this five statements. So let us give the proof for this. So let alpha is the any point be such that E of alpha is 0. So ultimately what we need to prove in this first task is to prove that E is non-zero. So what I am taking, there is some alpha in R such that E of alpha is 0. So I am just proving that for, or taking for some value, maybe it has a 0 value. And let us define this J alpha be the closed interval with endpoint zero and alpha. So actually this J alpha is an interval of the such type. Again, this E is a continuous function on J alpha. Therefore, I can say there exists A greater than 0 such that E of alpha, so E of t is less than or equal to k for every t belongs to J alpha. So it is a bounded function. Again, by applying the Taylor's theorem about the point alpha, so applying Taylor's theorem, f of E of x will be E of alpha plus E first derivative alpha upon 1 factorial x minus alpha plus E second time derivative upon 2 factorial x minus alpha square up to so on n minus 1th derivative of E at alpha upon n minus 1 factorial x minus alpha power n minus 1, and the last term is a remainder term, that is nth derivative of En is Cn upon n factorial x minus alpha power n. Now I'm putting x is equal to 0 here, and this is true for any x which is in interval I alpha, so in particular E0, and we know that E0 is 1. So as per this expression, it will gives me E alpha plus E1 of x, sorry, alpha upon 1 factorial x is 0, so it is minus alpha plus E2 of alpha upon 2 factorial minus alpha square up to so on E n minus 1 alpha upon n minus 1 factorial minus alpha power n minus 1, and the last term is E Cn upon n factorial, nth derivative of that, minus alpha raised to n. But what is E alpha? What we have assumed that E alpha is 0. So the first derivative of E at alpha is also 0. In particular, all nth derivative at alpha is 0. So this all terms will get cancel out. Only the last term is left, that is a remainder term, that is En, that is nth derivative upon n factorial into minus alpha power. If I take the limit, if I take first modulus, so I can say 1 mod 1 is less than or equal to mod of En of, but not less than, but it is equal to upon n factorial alpha raised to n mod. So I can say just mod alpha raised to n. But En is bounded by k. So I can say this is less than or equal to k times mod alpha raised to n upon n factorial. This will tends to 0 as n tends to infinity. and this will leads to a contradiction that 1 is less than or equal to 0. So hence I can say this is a contradiction. Hence there is no alpha in R such that E of alpha is 0. So this completes the proof of the first property. The second property, in that we have to prove that E of x plus y is E of x into E of y. It is kind of E power x plus y equal to E power x into E power y. So it's like this result. So for that I am fixing one point here. Let me fix y. Y be fixed. Since y be fixed, and using this above statement, we can say E of y is non-zero, because E function is non-zero function. So E of y can define as non-zero function. Now I am defining one function g from R to R as g of x is equal to E of x plus y upon Ey. So if I prove this g function is E function, then we are through. For every x belongs to R. Ultimately, I have to prove that E of x plus y is E of x into E of y. So I am just taking other thing. So this is a function, and in the parameter it is x. Now let us see what is the derivative of this. What is g dash of x? A g dash of x is E dash of x plus y upon E of y, because the derivative we have to take with respect to x. Y is a constant, so it is taken out, and the derivative of the numerator is the same. But derivative of any exponential function is gives you the same value. So it is E of x plus y is E of y. Now what is this function? Is a g function. And what is g of 0? G of 0 is E of 0 plus y upon E of y. So this will gives me 1. That means this g function is derivative in itself, and at the point 0 it gives me value 1. But we have proved that such function is only one function is possible, that is the exponential function. So uniqueness of that theorem, so I can say from uniqueness of exponential function, we say that g of x is nothing but the E of x for every x is in R. But what is g of x is x plus y upon E of x plus y upon E of y equal to E of x, which implies that E of x plus y will be E of x into E of y for every x y belongs to R. This is true. So this completes the proof for the second property. Now in the third property, I have to prove that for exponential function you can write down E power R. For rational number R is a rational number. So to prove that one should note that what is, if I take n is in natural number and x is in R, then what is E of nx? As per the above argument, that means E of x plus y is E of x into E of y, will gives you this is E of x plus x n times. So this is E of x plus E of x n times. So it will be the n into E of x. For every x and for every r. N belongs to n, and for every x belongs to r. This is Ultimately, we have to prove for rational numbers. So I am just trying to prove for now if x is equal to 1 by n in this quantity. So what we have proved it is nx is this. Now in this, if I put x is equal to n, 1 by n, then it is n into 1 by n equal to n into e of 1 by n. But this will gives you e of 1, and e of 1 we have did it is small e, that is Euler function, n into e of 1 by n. So this side it is this. So ultimately e of 1 by n is equal to e power 1 upon n. Due to this we can write. Because we can see that e is equal to e of 1. E of 1 we can write down n into 1 by n. And if I use this one, see what I have here, it is a product n times. It is a product n times. So this is power. So here it will be a power. Here it is a power. So this is I have written right. So this is e, then this is a e n 1 by n power n. So therefore e of 1 by n is e power 1 by n. So we have done the result for natural numbers, a number of the form 1 by n. Now let us prove for negative integers. So now if I consider e is minus m, if m is belongs to n, then as per this we can say it is 1 upon. See why we can say it is 1 upon, because e of 0, if I start with then m plus minus m I can write, but using the property of the exponential function which we can write down this is as this, but e of 0 we have 1, so that is e of minus m, it gives you 1 upon e of m, but e of m is e power m which we can write, and so this is we can write e power minus m. So now for any m belongs to z and n belongs to n, e of m by n, you can write down e of 1 upon n power m, that is e of 1 upon n we can write down 1 upon n power m, so it is e power m by n. So for any rational number r, we can say that is e power r for every r belongs to Q. Now the next task is to prove that it is a strictly increasing, which we already discussed, but let us give you very short proof for that. We have proved that e dash of x is e of x. And we also know that e of 0 is 1, which is greater than 0. And we already proved that e of x is not equal to 0 for any x belongs to R. And e is a continuous function. That also we know. So intermediate value theorem says that e of x is always greater than 0 for all x belongs to R. This is using intermediate value theorem, IVP. And e dash of x is e of x will tells you using the calculus that the first derivative e of x is greater than 0, that means e dash of x is greater than 0. The first derivative is positive, So the function is strictly increasing. The next things we need to prove the limit of e of x as x tends to infinity is infinity. And that can be easily done because we already discussed that 1 plus x, due to that inequality we have taken that 1 plus x is e of x. It's greater than, sorry, is less than e of x for every x greater than 0. If I take the limit x tends to infinity, what we can have, a limit x tends to infinity, 1 plus x is greater than limit en of x as x tends to infinity. But this will gives you infinity. And this quantity is bigger than infinity, so that's why this is limit of e of x as x tends to infinity is infinity. The second thing that we need to prove that limit of e of x as x tends to minus infinity is 0. So just replace x by minus z here. So that is limit minus z tends to infinity will be e of minus z equal to infinity. But what is e of minus z? Due to the things which we have discussed, that e of z plus minus z will be e of z into e of minus z. But e of z plus minus z is e of 0 and e of 0 is 1. So e of minus z I can write down as limit. This is z tends to minus infinity, I can write down 1 upon e of z equal to infinity. But 1 upon e of z is tends to infinity, so that means limit z tends to minus infinity, e of z will tends to 0. That proves that at infinitive it will goes to infinitive, at minus infinitive exponential function will goes to 0. And again, by intermediate value theorem, one can say that the range is this, all y which are greater than 0. This is the range of the exponential function, which we can done by intermediate value theorem. So these are the properties of exponential function and related to the exponential function. Using this exponential function, we can define logarithm function, power function, all sort of things is established using this exponential function. So if you have any doubt in this, then you can ask.